All right, y'all got the problems here for us to start the day. Once I get the attendance down, we can start walking through. All right, y'all, I'm gonna go ahead and start with these so we make sure we have time to discuss some of the new stuff that we're gonna look at. So the first one, right, we're kind of continuing from what we talked about yesterday with graphing exponential functions. Hopefully, one of the big things you notice there is I put a negative, but this time in the exponent rather than in front of our term, right? The other two are situations where we practice evaluating, but it's a little bit more involved with these, but I just want to make sure we're comfortable using our calculators, especially. The second one, you need your calculator, okay? With that said, before we jump into those, understand with this, we still have intercepts, okay? With intercepts in place, we could definitely go through and find them. You'll find that dealing with the y-intercept is something we can still work with, but it's not always going to be a value that you want to go and deal with from a like plotting the point perspective. Because remember, 2 to the negative 4 means, hey, I'm going to put that 1 over the result, right? So this would be 1 over 16 minus 8. The fun part there is now you have to have the common denominator where you do 16 times 8. So what's that going to be? 108? No, 128? Double check. So So you have negative 127 over 16, which is not necessarily something like, woohoo, let's plot that, okay? But they still have intercepts. Now, the problem we run into though with the x-intercepts is we're gonna have to discuss what do we do in this situation when it comes to solving. All right, that's gonna be the tough part. We're gonna be pretty limited on what we can do in some situations. Other situations, we can take advantages. What's another way to write 8? 2 cubed, right? Now, with that said, what we need to discuss then is if the bases are the same, do the exponents have to be the same, right? So let's go look at the graph and we'll be able to answer that. Okay, so that's where one of the things I want to look at as far as this graph is concerned. Okay. As we look at this first function though, what did I change? That wasn't supposed to happen. Where did I put it at, y'all? All right, let's do this. If we have time, we'll do a third one. I don't want to push it. I just talked about the negative exponent. I should have caught that right off the bat, huh? Sorry. There we go. We better now? Now, keep in mind, I want to do this one intentionally, right? Because of that negative exponent. Okay. With that said, though, make sure you see here that one of the important things we can look at is the parent function. I didn't ask for it, but make sure you see the parent function is 2 to the x, right? That base is very important. That tells me like, hey, I'm thinking 1, 2, 4, 8, and so on. On the negative side, 1/2, 1/4, 1/8, and so on. Okay. What are the transformations that I had with this one I started with? What's one of the things that stands out to us? It's not the 2 or the x. The 3, right? What's the 3 tell us to do? All right. It's a shift, right? Why is it up though?
Because it's not in the. Yeah.
Well, in this case, it won't necessarily always be parentheses. Just remember, it's the exponent is our parentheses, that group, okay? So since it's not in the exponent, that's how we can confidently be like, that's vertical, okay? Now, with that said, though, what is in the exponent that we have to be careful of? The negative, right? So that negative is there. So make sure you see here that that negative definitely has an impact, and that's going to just be a reflection as we've dealt with in the past. But make sure you see here, this is a horizontal reflection. What that means is once I take my graph of my parent function, which if we plot out those points, this is me just doing the parent function. All right. Took away my point. The parent function, right, looks something like this. Okay. Well, a horizontal reflection says to rotate it about the y-axis. So it's something like a y-intercept won't change, but as I zoom in here, what you want to do is take all these points and flip them over. So what you'll see in the end is that your graph's going to look something more along these lines now, which instead of exponential growth, what can we call it then? All right, because as we go left to right, it's actually going down. Now make sure you see here though, it still approaches that horizontal asymptote that we're going to talk about. Okay, now that's not our graph though, that's just me showing you the reflection. Our graph, right, the focus of it that we had this time is going to be at +3. How did we know it's at +3? What did we say we had? Had the shift up 3, right? So make sure you understand when you say shift up 3, make sure you go over there and say, hey, my horizontal asymptote is y equals 3 then. That's a nice thing about exponentials. Their horizontal asymptote is the vertical shift. Whatever that constant term is, that's going to be my horizontal asymptote, okay? Now what that means though from here is what we want to take the graph that we just discussed and go through that process. So this point here is one above my asymptote. There was no shift left or right. So if, like I was kind of doing the other day, you can put a little mark to show like, hey, that's technically like where the origin would have been before shifts. And then we can start plotting our points here as such. Make sure you see I'm not doing the quarter point, right? As I stated, yeah, we know it's going to get to a quarter. We know it's going to get to an 8. I just put the half point because, hey, that one's not too bad to graph. Okay. The main ones I said to focus on were at least the 3 integer values. That will set what's going on. Okay. Now, as far as our graph is concerned, we have exponential decay. All right. Some things that we can interpret from this. Okay. As x goes to infinity, so we're looking at the right-hand end of our graph. So this would be end behavior. As x goes to positive infinity, our function goes to our horizontal asymptote. Very similar to rationals. However, on the opposite side, where does this go to? Does it ever stop growing on the other side? Yeah, that one goes infinity, right? That's the thing about exponentials. One side's going to go up exponentially where the other side's going to approach the horizontal asymptote. So we want to be careful with understanding how to interpret that. So if we go to negative infinity, our function actually goes to positive, or it's rising is another way we can compare that. Now, the main one I'm focusing on, make sure you see this again, is how the horizontal asymptote affects our end behavior like we saw with the rationals, but it only affects one side of an exponential, not both. Is everyone okay with why we're saying this is decay? What sign was here then that would have highlighted decay for us before we graphed it? Yeah, that negative on the exponent, right? Anytime you have a single reflection, whether it be a vertical reflection or horizontal reflection, you're going to have exponential decay. Questions or concerns with this one though? Where this graph is coming from? Do you feel okay with that process then? Now I'm going to skip that one. We'll just do this one here. I want to do this one though to make sure you see another way you can write it out. What's standing out to some of y'all as you copy this one down? The fraction, right? This is going to be an area where I would say make sure you remember to rewrite that. That's going to be 2 to the negative 1 raised to the x minus 3. And then you can just say, hey, g of x equals 2 to the negative x minus 3. Now, it's not that much different than the last one. I will keep it with the shift down 3 just to make sure, again, you see it as a different problem when you look back on it. But the main thing I want you to take from this is if you get a function with that 1 over something, just remember you can rewrite that fraction as a negative exponent. That's another way that someone can put exponential decay into a problem. Now, this is important because a lot of times when you're dealing with applications, looking at a 2 is something we can use, right? 2 times something. What's another way to say that, hey, something grew by 2 times the amount? It's another term that we can use. Like people like to say, like, anyone ever made something with yeast? You want to wait till the dough does what in size? Rises, but doubles in size is typically what we say, right? Not every recipe says that now, but doubling, right? Well, 2 represents doubling, doesn't it? And the more 2s you have, the more times it doubles. Well, guess what? Half, if it's not doubling, it's taking something and find out when is it going to be half that size, right? So from a science perspective, when do we want to look at like how long it takes to get to half the amount? Anybody remember that term from science? Radioactive material has a decay behavior and we call it half-life, right? So the 1/2 would actually have meaning to us as we look at it, okay? With that said though, why am I drawing this first?
Because that's
That's a horizontal asymptote, right? Did we have any shifts left or right? So we can focus right there on that y-axis still. The key here to remember again is you have decay. So when you go to start graphing this, you start at the one above that kind of crosshatch that I made right there. But from here, why am I putting this at 2 and 4? Well, where am I getting 2 and 4 from? What's my base? 2, right? So understand this is just 2 to the first and this is 2 squared. But make sure you see I put it on the opposite side though because of the negative. Okay, that's the key to remember here. So over here though, that's where we'd see the negative. And then I can draw. That other one, I'll let you write it down if you want to do it on your own, but I just changed the base to a 3 to make sure we see, hey, it doesn't necessarily make everything different. Just make sure you watch your base. But I want to make sure to go through some of the application stuff with today as well, so. Do we feel okay though with we hadn't had a lot of horizontal reflection, so we okay with that? This is one graph though where we definitely see the difference. Square roots would have been another graph. Any questions? All right, so like I said, we could do this one. I'm not going to go through all of it right now. So if you want to copy it down, feel free to do that. Okay, but hopefully you see same pattern as I just discussed. Make sure you identify transformations. This one has a reflection, but that reflection was not a horizontal reflection, but a vertical reflection, right? So focusing again on exponential decay. What's going on here? Says something there. Nope. Gotcha. Now, I'm going to go back here. This is the other 2 that we wanted to look at, okay? Make sure you see here, though, this is like me taking one function. We're just plugging values in, is what it boils down to. I plug values in where the variable would be, okay? The first one could be something similar to what we saw just now. But one thing I wanted to make sure to put in there is be careful with how you do multiplication with the exponential term. So what you're going to see here is when you deal with this, make sure you see that you need to deal with that exponent first. Right, so negative of 3 becomes negative 3. Oops. Then I get 2 to the first. Once you deal with the exponent, which in this case 2 to the first is 2, then you can do the multiplication. Okay, but you need to do the exponential part first. That's, remember, PEMDAS. Please excuse my dear Aunt Sally, whatever it is that we need that you've been using to help you remember that. Make sure you understand exponents go before anything else other than grouping symbols. But that grouping symbol is why we did negative 3 plus 4 first. Okay. Any concerns with that one? Do I need to worry about rounding that one? All right, if it's a whole number, don't worry about rounding it. However, that next one probably isn't going to work out as nice, right? So this is the one you need to get your calculator out. And what you're going to need to see here is you're going to want to put in your calculator 150 parentheses 1 plus 0.12 divided by 4 close parentheses. It's very important that you're careful right here, because when you go to do your exponent on this one, you can easily make a mistake that is common. So we want to be careful here, okay? As you deal with your exponent here, make sure you put the exponent and then a parentheses. And then just go ahead and put 4 times 5 and close your parentheses. That way you ensure the 4 and the 5 are in the parentheses together, not just one of them. This is one of those areas where you can't put it in your calculator exactly how you see it on paper, otherwise it won't work properly, okay? Now with this, what we're seeing though is exponential growth. We know it's exponential growth because, well, I didn't put any negatives in this problem. Okay, no negatives in here, so we know it's exponential growth, so we better see more than 150. With that said, should we see a lot more than 150? Not necessarily a lot, right? It definitely needs to be more, okay? What is someone getting? Is everyone seeing this in their calculator? That's what you're seeing? I know one thing, like I said, as I work with students and looked at their tests and stuff, that how they handle, they write it right on their test, but then they give me the wrong answer. It's that exponent that typically is getting someone. So you have to be careful with that exponent, okay? Were you able to fix it?
That's the exponent.
You talking about right here?
Yeah, what's that?
That's the exponent key. So on the TI 30X2S, on the left side, it should have like that little caret looking key. Now, do I want to leave my answer like that though? No, so this is where like, hey, that we're going to get stuff oftentimes that's going to be irrational. Okay, so we're going to be forced into a situation where here we're actually going to have to write this in that approximated form. Always read what the problem tells you. That's going to be one of the keys there, okay? Make sure you read what the problem tells you. Any questions with that one? Do we feel okay with the calculator now? No, that's just one thing. When I put this on the test, part of the problem is making sure you know how to put your calculator. Okay, so keep that in mind. As we move forward though, what we want to see is where am I getting that from? Because this is going to be the next part. Okay. As we deal with exponential functions, one application that's compound interest, and that's something that, hey, for this situation, we can practice doing that, plugging stuff in. Okay. So I have a problem here where we're going to look at it and we're going to talk about the two different types of interest we're looking at and how we use those formulas. Okay. So make sure you see here again, our focus is going to be on compound interest. I have a couple formulas for us. Those are the two different formulas we
Do they
can.
have different names or they just both compound?
They're both compound interest, but they're different types. So they will have different names in a sense. Yes. What you're going to find here is you want to know both formulas. The problem tells you which one to use.
Because we just saw that in other two formulas in the next.
Yeah. I used one of these formulas, right? Is everyone caught on to that I used one of these formulas on that problem we just did? Now, as you finish writing these problems down, you write out the formulas and then write out the actual problem. The problem says $6,000 are being invested into a bank account that has an interest rate of 10% per year. Find the amount in the bank after 7 years if the interest is compounded monthly. So we need to figure that out, right? Well, do you want to use both formulas if that's the case? The answer is no, right? The reason we have two different formulas is for different situations. Okay, now let's highlight some similarities. What's something that both formulas have? But like variable wise,
P.
they both have P. What does P stand for, you think? All right, P is going to be the principal.
Oh.
Now, the principal is the initial amount. So like, what would be the initial amount for the problem we have right now? The 6,000, right? So make sure you see, like, when you look at that, like, hey, this particular number here would represent P. What's another letter they both have in common?
T.
They both have T, they both have R, right? They both have A, right? If P is the principal amount, what do you think A stands for? Huh?
Annual. Average.
How would you describe what it probably gives us? What is the formula going to do for us? For the question, right? How much is in the account after 7 years, right? So the way that we'll consider that then is the accumulated amount. Now keep in mind that A and P then are closely related. P is the initial, where A is whatever you have after time T. Another way that you'll see this written is like A of T equals. So it can be written in a function form rather than just A by itself. So keep that in mind. What do you think the T stands for? Right, T is time. Now, what is time measured in, y'all? Huh? I put monthly, but I also put 7 what? Years. So this is a tough one we have to be careful of, right? Which one do you think overrides is the question we have to answer, okay? So know that time is always going to be in years for these formulas. Is that clear to everyone? For the interest formulas, T is in years. Okay, so that's the same thing for both of them, right? What is the R going to be then? Right, R stands for the rate, and that would be our interest rate. Now we have to be careful. What form did I give us the interest rate in? A percentage, right? But what do we need to use when we plug it in? Decimal. So make sure you have that somewhere like in your notes, that make sure you change this to the decimal value. So one thing we would have to do would be like, hey, R is 10%. So I'm going to use 0.10. Okay. With that said, though, we could also see be like, hey, T is 7 years. And we said what? Sorry. P was the 6,000. We have a lot of information there. Now, what is the one thing that I haven't talked about then? The N, right? So this is going to be the distinguishing factor. So hopefully you saw there was a lot of stuff in common just now, right? But this N, well, definitely is one of the distinguishing factors between them to help you with that, okay? What you're going to find is the difference between the two formulas is how they are compounded. That's the big difference. So the first one here, whenever we look at this first formula, this is going to be compounded continuously, okay? So make sure you understand that this one here is compounded continuously. What letter stands out to you on this one that would help us remember continuously? E. Now, make sure you also know, did I say E was a variable? No, because E is not a variable. All right? You're going to want to find on your calculator where you see it should be probably something like E with the exponent button behind it, or E with an X right behind it. Go to your calculator now and do E to the first power. That way we can find. So make sure when you do that, though, you're getting 2.71828, and I think it was 1828 again. All right,
Just like, I think it's a second. Put the,
yeah, just put a 1, sorry. You don't normally need that, but for our calculators, E is always gonna have an exponent associated to it, so that's why you have to put the 1. Okay, now that's gonna be your kind of highlight that, hey, this is continuously compounded, is the E itself, right? The other one, when you see the letter N, that's gonna tell you it's not compounded continuously, but that's where it's gonna break up a year into parts. So what you're gonna see here, that's gonna say compounded N times per year. All right, so this is an important aspect of compounded N times per year, okay? So one's continuously compounded continuously, the other one's compounded so many times per year is what it boils down to, okay? So for my problem here, which one do I want to use is the big question,
the N times per year.
right? So because we have compounded monthly, right when we see that, we should be saying, hey, the formula I'm about to use is the second one we have up there. But when I do that, though, we need to highlight what N is, right? So if it's compounded monthly, how many months are in 1 year? Right? So make sure you see like, hey, when you see monthly, the N is 12. What if I said weekly? What would we use? No. How many weeks are in 1 year? 52, right? So understand weekly, it's how many are in 1 year is the key. If I said quarterly, how many quarters are in a whole? 4, there you go. So if you see quarterly, hey, 4. Semi-annually? No. 2. What if I said annually? No. What is 12? Monthly. What if I said daily? 365, right? Right, it's one of those though, you want to make sure you look, and you're not going to see all those in the homework, okay, y'all? Please keep that in mind. But we do want to make sure we look at those comparisons because we need to be familiar with the different ways it can be compounded. The big difference is though, is it telling me a certain number of times in 1 year, or is it telling me continuously? That's the big difference we have to separate. Since this one said monthly, I went straight to this formula here. I'm also going to go up here and make sure to put like, oh yeah, N is 12 though, because it says monthly. Well, guess what we have to do at this point? Plug everything in, right? So plug it in, and what does your calculator tell you? That's all you can do at this point, but make sure you go back if you're not sure how to do your calculator. That's why I gave us that first one to practice with. Now, while you're doing that, what would 12 times 7 give us? What did the 7 represent? How many years we're doing this, right? What does 12 represent? Months in a year, right? So if I do 7 times 12, what's that going to give me the total number of?
The year, no, the months.
The months in 7 years, right? So understand that when you see 7 times 12, if you multiply it out and be like, oh, that's 84. Well, hey, that's how many times it's going to compound, right? So with this one, make sure you understand that that 7 times 12 must be the exponent, because that's going to tell me how many different times it compounded during the course of 7 years, right? So whatever that base is, it's not necessarily a nice number, right? We know it compounded 84 times. I think it came out to like 2 something, and we could do 6,000 times that, and we get to the 12,000, right? We know it was 2 something though, because 6 times 2 is 12. Okay. That over the course of 7 years, it doubled in amount, right? So if you ever find an interest rate of 10% with an account that you're investing in, that's a pretty nice little interest rate there. Okay. If it stays,
I need 12,000. I'm supposed to put it together.
all right.
6,000 parentheses 1 plus 1 0.1 divided by 12.
Close parentheses. Then hit that exponent button. That, remember, it looks like this. Yeah, you could put 84, but if you do 12 times 7, make sure 12 times 7 is in parentheses. Yeah, and you've got something a lot smaller, right? Well, actually a lot bigger because it multiplied by 7. But that little exponent button, but like I said, I'm pretty sure if I remember off the top of my head, it's on the left side of your calculator there. That's how we get that to the proper spot. Okay. You'll find like on a computer, if you ever need to type an exponent, it's the caret key. It's the same key we would do typesetting exponents. Got it. All right, well, let's put our skills to use, right? Y'all ready for this? Oops, not that. There you go. Let's do them all. Huh? They have some on the home. It's not going to look like this necessarily, though. I think some of them might look like this. Now, things I would tell you is make sure you see we're trying to find A in all of these, right? So make sure you identify all the other variables, knowing we're looking for the amount. And we know that because it says find the amount. So let's make sure we're identifying all that stuff. So what does the 8,000 represent for us here? All right, that'll be our P value. What is our R value here? All right, so how do we want to write that though? 0.09, right? Be careful with those single digits, right? Put the 0 first. Be careful with the percentages in general. If you get stuck, just remember divided by 100, and whatever the percentage is divided by 100, because the percentages are out of 100. Okay, so 9 divided by 100 is where you get 0.09. Okay. What is T for all the problems, thankfully? Right, we're trying to find the amount on all of them, right? And it says, hey, for all of them, they could have just put 15 at the top, but this person put it with each part separately. Make sure you see, though, for all of them, T is 15, okay? Now, what I recommend here is just make sure you go through your calculator skills. Remember using the arrow to go back up to the formula that you have there, because the only thing that changes then for these first 3 is the end value, right? What did we say we should use for annually? How many times will that occur in 1 year?
Well,
So we have n equals 1, quarterly was 4, and monthly is 12. Okay. But what you want to do is make sure it's go through. I'm going to put the values down, but make sure you get the values with the same formula, right? It's the same formula we just did. The last one, we're going to use the other formula. Okay. But let's make sure we're comfortable with that first formula. Yeah. What decimal place should we round to with money?
this-
Yeah. So for money, just go to second unless it says otherwise. Okay. Are we getting to these values though that I put up? Are we in agreement? Because the point of this is making sure you're doing your calculator and you're getting these numbers. Okay. Let me know if I mess up in my rounding. I added one more though, just for the sake of conversation. You didn't need to do daily, but if you want to see what happens, go ahead and do your calculator. Is there any concerns with getting to these values that I could clear for somebody? All right, what did you put for P? What did you put right behind the 8,000? All right. .09 divided by what? And it's divided by 1 that time, right? But not all of them are going to be just 1. Yeah, divided by 1, and then 1 times 15 is our exponent. Now, what do you notice about the amounts as I go down the list? They got bigger, right? What made them bigger? Right, so the number of times you compound, as the number of compounding goes up, the amount that you get overall goes up, right? What do you notice about that amount though, as it gets larger and larger? And I put up daily at that point, it would be 365. Does it just grow without bound, just keep getting bigger and bigger and bigger and never stop? Like if you look at the difference of these numbers, as I go from one to the next, does it change much from this one to daily? Comparatively speaking, doesn't it change more between these two than it does these two? First one, it was over $1,000 difference, right? Or these last two, it's just 150 or something like that. That's different. Yet this one had the biggest jump. It went from 12 to 365. Okay, so keep that in mind that the number of compoundings will increase the amount you get, but there's kind of a limit to the, more compoundings is, yes, better, right? But the number that we get to kind of changes, right? If I wanted to, though, we can go to half a day, so 12 hours, we could do hourly, we can do every minute, right? All that grows to the word continuously, right? As we deal with that, as we increase our number of compoundings, it gets to a point where, hey, we're just going to call it continuously. When we get to the continuously, that's where we're going to say, hey, now we have a new formula. This is where the second part of your calculator is going to be important, because now you have to use that E key. So as we deal with this one down here in your calculator, what you want to do is put it as the 8,000. And you're going to put times your E, which is, I don't remember exactly where it is. You have to hit shift to get to it. No, second to get to it. Now understand with that one, it should put the exponent right behind it already. It's going to put the exponent button with the parenthesis for you. So once you get there, understand all you need to do then is R times T. The same R and T that we were dealing with, 0.09 times 15, close your parentheses, you're good to go. I think with that one, what did I get? And here you'll see that going from daily to continuously itself is even smaller of a change.
So if the word continuously is up there, you're gonna use A equals P.
That is the key. If you see continuously, hey, I need to use the whole of the formula. So it's better, I think it'd better default by starting with the compounded in times per year formula, right? But once you see the word continuously, hey, that's that other formula with E involved. All right, now mathematically, where that comes from, as I kind of talk about, when you look at calculus, right, you'll have better language to describe that transition, okay? They're both interest formulas. And this formula comes from the other formula, right? As you can see here, it built towards that value. That's one thing I wanted you to see here, that as I went from daily to continuously, there really isn't much of a difference of what, maybe $5 total. Okay, so keep that in mind. Is there any concerns with calculators before we move forward? That's definitely my highlight here, is making sure we're comfortable. Now, here's something that this builds towards. This is going to help set us up for what we need moving forward. Okay. So as you see here, I have a compounding continuously. When my question is, when will the amount double? All right. When I put that amount doubling, what I'm saying is let A of the amount equal 16,000, right? Now, what you're going to find here is, though, is if I write out the work, we'll have 16,000 equal to the 8,000, E to the 0.09 T. right? Continuously makes the solving a little bit nicer because I don't have to write the parentheses grouping every time. When you deal with this though, what should we divide by on both sides to get the exponential part by itself? 8,000, right? What's 16,000 divided by 8,000 though? Huh? Not 2,000, just 2. The key though is the 2, right? Understand, I said double. Well, the 2 represents that. I wanted to figure out when it doubles. Okay. Now the problem is here. What in the world do I do with this? Okay. What you're going to find is this is where we can go back to our graph. Okay. And I'm going to talk about that. All right, so let me pull up a graph. We said 8,000, right? We said 0.09, right? All right, once I shrink my y-axis some, what shape do you see there that we should recognize? What graph is that we've been working on? I can go put this over here if we need to. It's exponential, right? Does everyone agree that that's just an exponential graph? I just had to. Let me change the color of the asymptote real quick. All right, so as I deal with this, this is our exponential here that we've been looking at. Okay. What is that y-intercept at right there, y'all? 8,000, right? So understand the initial amount is what we call a stretch. And remember our original point was 0, 1. Well, 1 times 8,000 puts it at 8,000, which is why I had to do all that zooming out and then shrinking of all that y-axis stuff to actually see what's going on. Okay. Now, with that said, when we talked about graphs, there was a couple of tests that we did. Right? What were the tests that we did to describe the graphs? What notation do you see kind of really tucked up in the corner there? I can't make it bigger. I wish I could make it bigger. Oh, wait, I can't make it bigger. What do y'all see up here at the top, right next to the green dot? F of X. What is that notation? Function notation, right? It's function notation. Now, ignore the fact that it says X right now. I did it for the thing to graph it like I wanted it to, okay? The key is if I wanted to know if it was a function, what can I do? Vertical line test, right? We can go through here and use the vertical line test to show that this is indeed a function. Each X, there's only be one Y. What was the other test that we did? So if I go back to the horizontal line test. Now, what was the difference, right? Because if I look at this, the vertical line test was great. Okay, as we can see here again, hey, that's definitely a function. Every one of them works out well. What did the horizontal line test do for me that was nice?
Say it was a function.
No,
Or no, it was 1 to 1.
if it was 1 to 1. And what do you notice about exponential functions here?
Yeah.
Does everyone see that it passes the horizontal line test? So as we deal with this, make sure you understand that exponential functions are 1 to 1. Now, the reason that we like that, remember that for each X, there's only one Y, but that's a unique relationship. That means this Y value, particular with this point, will never be used again. Well, if we go back to our graph here, I asked when we'll get to 16,000, right? How many times does that horizontal line there cross my graph again?
Um,
How many times does that horizontal line that I just drew here in blue cross my graph? And so how many solutions will we have then for when the amount makes 16,000? One solution. We can have the confidence that there's only one solution now. Does everyone see that? Now, the nice thing is we can just go over here and get that solution. So as you see there, if you could read it, it says 7.07, which if you remember, I already wrote it out for you. So it has a solution, but understand the only reason we can have the confidence to write this is because it's one-to-one, and I can use a graph to get that. That's where I'm getting that from, is a graph. Is that clear to everyone? Now, why is that important? Because I can then answer a lot of questions like we see here. When does it get to 12,500? Now, the thing is that we're limited to right now is I gave you a graph. Okay, we can use the graph and that software can find it for us. So if we wanted to, we can go back to the graph. Instead of doing the 16,000, we could just do 12,500. Okay, so let's go look at that real quick. If I change 16,000 here to 12,500, I can highlight the intersection of those two things. Again, I know it's kind of small, y'all, but make sure you see there is a solution. If you want to write the solution out, it's 4.96. Okay, what does the 4.96 represent to us? But like, what's the measurement we're referring to right now? What was the question I asked? When, right? So that's a number of years, right? So 4.96 years, almost 5 years, would answer this one. All right. Now, what I want you to take from this aspect that, hey, I got to be able to plug in and work these things out, but know that we need to be able to reverse that conversation. Where did I see that first question? Well, let's go back to our intercepts argument. Intercepts, intersections, those are kind of similar, right? So I could easily put like, hey, when does this get to 32? Okay, but typically we want intercepts when we're graphing, okay? Compound interest formulas, maybe you have a financial goal, right, that you want to meet. That would be what kind of determines what you set it equal to, okay? But what I want you to see here is because we know something is one-to-one, when we get to this situation here, if we can ever make to where both sides have the same base and they're one-to-one, what else must be true? If the bases are the same, the only other part we have is the exponent, right? What must be true about the exponents? They have to be the same, right? So this is where we'd be like, hey, we know that exponentials are one-to-one, so we could write one-to-one here because we got the bases to be the same. And this allows us to solve an equation. And I find that this actually does have an x-intercept at 7. Okay. Now, make sure you see here, 2 is a lot nicer to work with than E. Okay, I use the compound interest formula to bridge this though, so that we can be comfortable with our formulas and using our calculator for 1. Okay, so please keep that in mind. The second aspect though is by going to the graph, we're able to kind of see some of the things, how that impacts the graph. And I was able to just show that, hey, if you do just 2 lines crossing, then you could find the intersection on software. What that's allowed me to do though is make sure I bring up one-to-one. So make sure you see here, the horizontal line test doesn't go away. That's something we always want to be ready to use, that like, is my function one-to-one? Since exponentials are one-to-one, this allows me to find intercepts sometimes. Not all the time, right? Because this just happened to be 8. If it wasn't 8, it was 9, I couldn't do anything. It only worked because it was 8. So keep that in mind. But I can get to solutions. That's a nice thing. What was the other thing though a function has if it's one-to-one? What did I ask you to show me on that second test? By graphing and showing me it was one-to-one, I was asking you to determine if it had something. What was it? You don't keep your test with you at all times? It was the last problems on the second test. I said, determine if the functions have a what? an inverse, right? By knowing that something's 1-to-1, we know it must have an inverse. Okay, exponentials are important, but what we're going to find out is its inverse is probably something that's even more important mathematically. Now, of course, we need both of them, right? So we can't say one's, more valuable than the other, but the inverse is definitely something that we need to talk about. That's what we're going to start with tomorrow. So make sure you come tomorrow to see the aspects of exponentials and the fact that they have an inverse. What you're going to find, it's a new function. You may have never seen it before. Okay, so we need to make sure that we set the foundation for that. Okay, so tomorrow we're going to jump into logarithms, which is going to be built on the inverse of exponentials. Okay, any questions?
Can I get the other side?
The
That side?
this one, right? Now remember that one, I graphed it on GeoGebra to make sure to show you it had solutions. Okay, that was my main thing, in that it helped reinforce the 1-to-1 aspect of that. That's definitely an important part that I wanted to establish today. Just know that tomorrow when I talk about logarithms, the main thing that we want to keep in mind, inverse of an exponential. An exponential is an inverse of a logarithm. All right. Any questions as we head out? All right, then have a good day and I'll see you tomorrow.